All right, so let's take a look at our last section from chapter 7, which is 7.6. And being the last section, a lot of times that last section really ties in all kinds of stuff that we've learned throughout the chapter. Okay, so things that we need to know in this section that we just went over, the ASTC diagram. So that's going to be important. Inverse trig, okay, how we get rid of a regular trig function. A couple algebra concepts like factoring and quadratic formula, and we'll review that if we need to. And identities. So any of the identities that you see here, along with, I believe, the double angle identity. That's all different things we're going to pull from in this lesson. All right, so what are we doing? Well, we're doing something that we've kind of done before, solving equations. The difference is when we solve equations now, we're not going to be doing anything graphically. So we took the graphing calculators out. We won't need them as far as graphing. You will need them to do like second inverse and stuff like that. Okay. So some different techniques that we're going to use. Factoring. And there's two kinds of factoring. Okay, one kind of factoring is if you had something like this. 3x squared plus x. And you factor out the GCF. Okay, that's the easy kind of factoring. You just look at what they both have in common, and you factor it out. Okay, the harder kind of factoring is something like, let's say, x squared plus 6x plus 5. Okay, that's where you factor something into two sets of parentheses, like x plus 5, x plus 1. Okay. So we're going to be doing both of those kinds of factoring, but we're going to be doing it with trig. So if we don't understand it with algebra, then trig is not any easier. All right? So that's going to come up. And writing something in terms of one trig function. So we've done that where we changed the sines and cosines, or sometimes we changed different trig functions, but the point is one trig function. Okay. What that one trig function will be, well, depends on the problem. Okay, but one trig function is important. And lastly, quadratic formula. So if you don't remember that, well, actually, you tell me the rest. What goes under the square root? Yep.
B
minus
or negative B.
Squared.
Squared.
squared
That's 4 is
minus 4ac
Into it.
Over 2a. Yep. So we're going to use that formula today. We've only used it, or you've probably only used it with like an algebra equation, but you can use it with a trig equation exactly the same way. That's 2a. All right, so as far as notes, there's really not much else I can tell you. We've done everything you need to do these problems. We just got to put it all together now. All right. So let's look at examples. Okay, here's our first one. Okay, we're going to solve that equation. That equation kind of fits a type of equation we've talked about. We talk about it a lot in Algebra 1. And we talked about it earlier this year as well. That kind of looks like what type of equation? Yeah?
Polynomial.
Okay, it is kind of looks like a polynomial. Specifically, what kind of polynomial?
trinomial.
Okay, it's a trinomial. And how about based on the degree? Yeah?
Quadratic.
It's a quadratic. It looks kind of like a quadratic. Something squared, something not squared, and then a constant. Right? And there's one problem with it. The problem is this. There isn't just one trig function. We have a mixture of sines and cosines. When you have something that fits this pattern, and you have three different terms, to get it so you have the same trig function everywhere, you are going to substitute for the thing that is squared. Always. That's how you always do it. look at the one that's squared, and you're going to change that one. You're not going to change anything else. And the way that you're going to generally change something that's squared is you are going to use a Pythagorean identity. So I copied the Pythagorean identity you need for this one. It's sine squared plus cosine squared equals 1. So what does that mean cosine squared would equal?
1. No.
1 minus sine squared.
1 minus sine squared. And that is what we're going to change that to. We're going to change cosine squared to 1 minus sine squared. Everything else is going to stay the same. So let's do that. Because you're substituting in something that's going to have 2 terms in it, if you have a number in front, it now becomes a distributive property. So you need to leave parentheses around what you substitute in. Okay. Any question on what I substituted in at that first step?
So you just put in the 1 minus sin squared, and then you substitute for the cos to an x on the top.
Yeah, I substituted 1 minus sine squared in for cosine squared.
Okay.
Yep. Using the Pythagorean identity from section 7.4. All right, now we have to do a distributive property. So let's do that. We have 2 times 1 is 2. 2 times negative sine squared is just negative 2 sine squared. Okay, and if you're wondering, well, what good did that do? Look at the trig function we have. Every term that has a trig function in it now, it's what trig function? It's all sines. One's a sine squared, but that's just like having an x and an x squared. It's going to be quadratic. Okay. So let's rewrite that how you would write a quadratic. You'd put the squared term first. You would put the term that's not squared second, and you would put the constant last. What's 2 plus 1? We can combine that together. 3. And that's your first step. Okay, get it all in terms of sign. Now, the next step is, because it has something squared, the same something not squared, and a constant at the end, that is a quadratic type of problem. So let's see if we can factor. When you factor something, we always like this to be positive. Okay, we don't generally ever factor when that first thing is a negative. So what could I do to get rid of this negative right there?
Multiply by a negative, or multiply the whole equation by a negative.
Yeah, you could multiply everything by negative 1. So what's going to happen? The sign of everything is going to switch. Right? So that becomes a positive. That becomes a negative. That becomes a negative. And you do have to multiply 0 by negative 1 as well, but
It's 0.
it stays 0. All right, now, factoring that problem is exactly like factoring this problem. There's no basic difference in doing this or doing that. They're the same basic problem. So let's try factoring it like this first, and then we can try factoring the other one. This is the kind of factoring where you're going to get 2 terms. What's going to be my first term in each set of parentheses? Okay, an x and
Negative
2x.
2x. Okay, so a 2x and an x. So when we factor the one on the left, it's going to be a 2 sine and a sine. It's going to be the same idea. Okay. Now let's figure out our pluses and minuses. I've got a minus and a minus. What does that mean I need down below?
A plus and a minus.
I need a plus and a minus. So let's try I'll try them in that order. If it doesn't work, we might have to switch. And now I need two numbers that multiply to give me 3.
1 and 3.
Let's try 1 and 3.
Yeah.
Let's FOIL that out. You get 2x squared. That's good. But what's 2x times negative 1?
Negative 2x.
And what's 3 times x?
3x.
What's 3x and negative 2x?
1x.
Positive 1x. No, we want negative 1x. So what do we need to do?
Swap this with 1. Or swap the signs.
Swap the signs, not the numbers. That would make a difference here. Now, you get positive 2x, take away 3x, negative 1x. Perfect. Now let's do the same factoring over here. We're not going to have 2x minus 3. We're going to have what for that first factor?
2 sine
2 sine
x
x
minus 3.
minus 3. And my second factor?
Sine x.
No. And if you check it, 2 sine times sine is 2 sine squared. 2 sine times 1, that's 2 sine. Take away 3 sine. 2 take away 3 is negative 1. Perfect. And negative 3 times 1 is negative 3. All right, so that's the hard part, factoring it. Now, once you factor something, what do you do with each factor? You make them equal 0. So there's your first answer, or there's your first equation. And your second one. So the first thing you want to do is get sine x alone. How would you get sine x by itself there?
Divide by 2.
Add 3.
Add the 3. Yep.
And then divide by 2.
And then divide by the 2. Okay. Let's do the same thing over here. How would you get sine x by itself on the right?
Subtract 1.
Just subtract 1. Now we're at the step where we've got a trig function. The variable is inside it. We've got to get rid of that trig function.
Inverse sine.
Yep, take the inverse sine. So lots of things coming together. So take the inverse sine of each side. Inverse sine and regular sine cancel. And let's take the inverse sine of 3 over 2. What is 3 divided by 2?
1.5.
1.5. What's the highest you're allowed to do inverse sine with? 1.5 is too high.
Is it
Negative 1 and 1.
Negative 1 to 1. Is 3 over 2 between negative 1 and 1?
No.
Okay, so
No.
that's not an answer.
So from this part of the equation,
That's not an answer.
there's no solution. So this part doesn't help us.
Okay.
This part might.
Yeah, because that is not an answer.
Let's try the inverse sine on each side. And we said between negative 1 and 1, and that is, so this will work. So take the inverse sine of negative 1, and we get an answer of negative 90 in degrees. Now, directions specifically said to write answers between 0 and 2 pi. That means 2 things. 1, they don't want degrees, but I usually do degrees first. And 2, they don't want negative numbers. How can you make negative 90 a positive number?
Add 180. Add 360.
Add 360. Yeah. And if you add 360, what does that become?
270.
270. Okay, so we made it positive. That's one thing. The other thing is they want it in radians. What's 270 degrees in radians?
3 times 2.
Yep, 3 pi over 2. And that's the answer, 3 pi over 2. Now, 270 degrees. Think about this for a second. Is 270 degrees in a quadrant?
Yes.
No.
No, it's on an axis. Because it's on an axis, you don't need to worry about that term. If it was in a quadrant, then yes. Then we got to get into that. But for the first problem, because it's on an axis, don't worry about it. Okay, so 3 pi over 2 is your answer. If you had done this in radians, because you might think, well, why not just put your calculator in radians, right? Well, what's going to happen if I do this in radians?
You're gonna get a different answer.
What kind of answer am I going to get?
Decimal.
I'm going to get a decimal. Do you know that that's
Equivalent.
equivalent?
3 pi over 2. No.
Yeah, you might not know that, right?
No.
So do it. That's why I always say do it in degrees first. Okay. That number that I just got, that negative 1.57, that's actually equivalent to negative 90. That I would have had to add 2 pi to make it 3 pi over 2. Okay, but it's a lot easier to do the arithmetic in degrees and then change it at the end. Okay. Any questions on that one? So that's a pretty typical pattern. Substitute for what's squared, factor it, and then set each factor equal to 0. Okay, let's try another one. So we're going to find all answers between 0 and 2 pi. What's different about how this equation is written compared to how that one was written?
Not equal to 0.
It's not equal to 0. So let's make it equal to 0. What could we do to make it equal to 0?
Subtract the right side.
Okay, we could subtract the right side. There's 2 things to subtract. Or we could just subtract the left side. Right? There's only 1 thing. Now, you might say, well, wait, if you subtract 2 sine squared, you said earlier you always want sine squared to be positive. Ultimately, yes, I do. But put this on the right side for now, and watch what happens. You might think you're making the squared term negative, and right now, temporarily, you are. But it's not going to stay that way. Okay, watch what happens. Okay, so I put the 2 sine squared on the other side. Now, it's almost like a quadratic, but something's wrong with it. What's wrong?
There's a negative on the side.
So the negative is okay. That's going to end up going away. You'll see in a minute.
Listen.
Okay,
Is that
yeah.
equal to cosine?
We have a sine and what else?
Cosine.
We have a sine and a cosine. That's like trying to solve an equation with an x and a y in it. You've got 2 different things going on. So we got to get rid of one of them. Which one am I going to get rid of?
The cosine.
The sine.
Well, I told you to always substitute for the one that's what?
Squared.
Squared. So you're going to substitute for that. So you're going to have negative 2. You're going to fill something in. And everything else will stay the same. Now this time I didn't write down the identity. What does sine squared equal? The identity was on the last page.
Negative cosine plus 1? Sine squared.
Yes, that is true. Can we write that a little easier than negative cosine squared plus
Cosine
1?
squared plus 1?
1 minus cosine squared.
Yeah, let's write it as 1 minus cosine squared. Okay, now what do we have to do with that negative 2?
Distribute.
Distribute. So watch what's going to happen. What's negative 2 times 1?
Negative 2.
And what's negative 2 times negative cosine squared?
Positive cosine squared.
That's why I put the cosine squared where I did.
Wait. There we go. I was going to say, wait, should there be a 2 in front of cosine squared?
Okay? So whenever I have to substitute, I always make the squared term negative, because I know when I substitute, it's going to change to positive. Okay, now it's exactly the same as the last problem. Put it in descending order, so squared term first. Term that's not squared, second. And what's my constant going to be?
-1.
Yep, -1. Okay. Yeah, not every problem is going to be factorable, but I will tell you this one is. Okay. If you have trouble factoring it because the trig is confusing, then off to the side you can think of it as 2x squared plus x minus 1. But let's see if we can factor it with the trig. What would be my first term in each parenthesis?
Cosine.
So I would have a cosine over here.
Two cosine.
And what over here?
2 cosine.
Mhm. So that's like a 2x and an x. We have a 2 cosine and a cosine. What about my pluses and minuses?
2 minus sin.
Well, if you do a minus and a minus, a negative times a negative is a what?
Positive. So plus minus.
Positive. Yeah, so we need a plus and a minus. May have to switch those. And two numbers that multiply to give me 1.
1 and 1.
Okay, let's see. 2 cosine times -1, that's -2 cosine plus 1. -2 plus 1 is how much?
-1.
-1.
So I need to swap them.
We got to swap the signs. So plus, minus. Now you get +2 cosine, take away 1 cosine. Perfect. Okay, so now we factor it. Now there are going to be some problems in the homework that start you at this step, and people get confused. If they start you with this, they've just done the substitution, the distributive property, and combining like terms for you. What do you do once you have it at this step? Take each factor and do what?
Set them to 0.
Set them to 0. Now, there'll be some problems in the homework that start you at this step. They give you 2 equations equal to 0, and now you just have to solve them. Okay? How do we get cosine x by itself on the left?
Add the 1 and then divide by 2.
Okay, add 1 and divide by 2. And now there'll be some problems in the homework that start you at this step. That's the simplest they can start you off with, because there's only one step left in that problem. Okay. This is the most complicated they could start you off with. All right, so there's that one. And the one on the right,
Cosine x equals -1.
-1. Okay. How are we going to solve both of them?
Take the inverse cosine.
Take the inverse cosine. Yep. And if you're taking the inverse trig of a number like 1, -1, 0, 1/2, √3/2, √2/2, any of those numbers I just said, you're always going to get a nice answer. So if this is a number that you remember seeing on the unit circle, it will come out nice. Okay, so numbers that have square roots of 3, square roots of 2, 0.5, 1s, -1s, and 0s. Okay, that's what you generally look for. So I know this is going to come out to a nice answer because it's a 1/2 that I'm doing inverse cosine of. So on my calculator, inverse cosine. I know they want the answer in radians, but I'm going to do it in degrees. And then I'll fix it. Okay, 60 degrees. Now, 60 degrees. Is that in a quadrant or is that on an axis?
Quadrant.
That's in a quadrant. So now 60 degrees is my reference angle. 60 degrees is in which quadrant? Okay, I got that one. We're looking for where cosine equals a positive number. There's somewhere else here that cosine is positive.
4.
Quadrant 4. Now, there's a formula for quadrant 4.
360 minus reference.
360 minus the reference angle. And 360 minus 60 gives me
300.
300. Those are my two answers. I need to change to radians, but now that's not as bad. I'd rather do all the work in degrees up front and then switch to radians at the very end. What is 60 degrees? Yep. Yep, pi over 3. Now, the easy way to get 300, how many times bigger is 300 than 60? It's 5 times bigger, so just make that 5 times bigger. Again, if you did this in radians, are you going to recognize the decimal 5 pi over 3? No, never. So do it in degrees first. Okay. So there's 2 answers, pi over 3, 5 pi over 3. And let's do the last one. What I like about 1s and negative 1s, they're always on an axis. When you're on an axis, you don't have to worry about ASTC. So inverse cosine of negative 1 is 180. And that is on an axis. What's 180?
Pi.
Pi. Yep. So those are your 3 answers. Pi, pi over 3, 5 pi over 3. Or degrees, 60, 180, 300. Okay. Any questions on that?
How did we get 3 answers again?
Well, we got 2 answers when we did inverse cosine of a half, because we have the ASTC chart. So we got 60, and then we had to do 360 minus the reference angle. So that gave us those 2. And then this one on the right, I just did inverse cosine of negative 1. But that's on an axis, so I did not get a second answer. If this hadn't been a negative 1, if it had been like negative root 3 over 2 or something different, I could have gotten 2 answers here. So I could have had 4. Yeah. Yep.
You just had to make this.
Okay. Any question on that one?
So we got the 181 from the inverse negative 1?
Inverse cosine of negative 1.
Okay.
Yeah, I just typed it in. I did not write down that stuff. I could have. All right. So just a reminder. You're basically finding where 2 trig functions are crossing, right? Like in this problem. If you put this in y1 and you put that in y2 and you calculated the intercept, you would get these answers as decimals. But if you zoomed out, how many times would this graph and that graph cross each other? If you could zoom out forever.
Infinitely.
Right, they would cross infinitely many times. This is just where they cross in the first cycle. That's all this is. So I want you to remember that even though we're not writing plus the period times n, there really are infinitely many answers. This answer repeats, that answer repeats forever, and that answer repeats forever. Every single cycle. Okay, but we are, in this section, we are not writing our answer this way. Okay, that's all I want you to remember. So you don't have to really write that. Is there any question on that? Okay, so we usually put plus the period times n. We're not. Okay, so let's find all the answers just in the first cycle. 0 to 2 pi. That's what we've been doing all along. Okay, any suggestions what I do first here?
Make it equal 0?
Okay, we could make it equal to 0. There's something else we're going to have to do that we've done before. but not today. But we've definitely done this. And you could either do what I'm thinking of first, or we could do what you said first. It doesn't matter.
Make tan equal sine divided by cosine.
Yeah, let's do that first. Let's make tangent sine over cosine. Now that creates a fraction, which I don't like either, but at least it's sines and cosines. How could I get rid of having a fraction on the left? Yep, by what?
Cosine x.
Multiply by cosine x, and watch what happens. That's gone. And we get sine x equals, and what's on the right side?
Cosine squared.
Now you have an equation where one trig function is squared, the other one is not, and they're different. Look at the last problem. One trig function is squared, the other one is not, and they're different. It's exactly the same setup now as this problem. So now we got to do what we did from there down. Okay. So now we want to get it equal to 0. Are they all the same trig function? No, we're going to end up substituting. So what side do you think we want to have the cosine squared on? Yeah.
The right side.
Left.
Yeah, we want to put it on the left. We want to make it negative. Because remember, when you substitute, the negative is going to cancel. If you don't do that, it just means you're going to have to do an extra step. You're going to have to divide everything by -1 to fix all that. Okay? But if you put it on the left, you're saving yourself a step. Now, substitute. What is cosine squared?
1 minus sine squared.
Yep, 1 minus sine squared. And what do we have to do with that -3? Yep, so let's do two things at once. Let's distribute it and put it in the right order. So I'm going to do that part first. -3 times negative sine squared. That's positive 3 sine squared plus sine x. And what's -3 times 1?
Negative
I'm going to put that at the end. Any question on that step? Okay. Now, you can try to factor that, but that problem is not factorable. Yeah, you're not going to be able to factor it. So what else can we do to solve a quadratic besides factoring?
Quadratic.
Yep, you can do quadratic formula. Remember, A, B, and C are all numbers. What's A?
3 sine 2x.
3.
All numbers. Yep. So A is 3. B,
1.
1. And C,
-3.
-3. So now, let's write that if it were like an algebra problem, algebra 1. You would have 3x squared plus x minus 3. What are you solving for in that equation?
X.
You're solving for x. Where do you see the x on the left-hand side? Like exactly what you said, just x.
The positive x right in the middle.
Right in the middle. So one thing to understand is when you are doing quadratic formula, you are setting what's in the middle equal to, and then you do out your quadratic formula. It's always, whether or not you do that, but it's always what's in the middle equals, and then -b plus or minus, all that stuff. So now let's go over here. We are not solving for x in this problem, because there is no x in the middle. What's in the middle here? Sine x. So we have what's in the middle equals, and now we're going to do our quadratic formula in that box. Because we don't have x, What does that mean we're going to have to do at the end to get rid of sine?
The inverse sine.
Yep, that's going to be our last step, inverse sine of the quadratic formula. Okay, so now let's do the quadratic formula, and that part's exactly the same. Negative b plus or minus square root of what comes next?
4. Oh,
1 squared.
1 squared
Plus 4.
minus
Minus 4 times a times c.
4 times a times c. It might become a plus, but it's not a plus yet.
Divided by 2a.
Divided by 2a. Okay. So that's sine x equals minus a minus. Yes, that does become a plus. What's 4 times 3 times 3? Plus 1.
37.
37. Yep. Okay. So if you were doing quadratic formula on the problem on the right, you'd be done.
Isn't it 36?
Plus
So
1.
37.
Oh, plus 1.
Plus 1.
Okay.
Okay, so if you were doing the problem on the right, that's it. That's your answer. But for us, to get x by itself, we have to take the inverse sine. Okay. Let's split that into two problems. So it's the inverse sine of negative 1 plus root 37 over 6. I put that way too close. And the other problem is x equals the inverse sine of what's going to go in the parentheses in the top here.
Minus square root of 37.
Yep. So I just split it into two rather than using plus and minus. So now we can see it clear. It's two separate problems. Let's start with this one on the right, on the left. Now, negative 1 plus root 37 over 6. Is that a nice number?
No.
No. I'm not going to get a nice answer when I do this problem. Doesn't matter if I do degrees or if I do radians. That is not a nice number. So if they want radians, then I'm going to put my calculator in radians because I know it's not coming out nice. Okay? So let's do the inverse sine of negative 1 plus root 37. So it's going to do the top first, and then we're going to divide by 6. Yeah.
Did you split it into two equations because of the plus minus?
Yes.
Okay.
Yeah. Okay, so let's write that down. We got negative 1 plus root 37 over 6. I think you want to type it just like that. But let's do it in radians. Okay, 1.01. Again, doing it in degrees, you wouldn't have got a nice answer either, so it doesn't matter. 1.01. Is that answer in a quadrant or on an axis? Definitely in a quadrant. Yeah, it's not a nice answer. So think in radians now, not degrees. This is 0. Pi divided by 2. Pi. 3 pi over 2. Those are my decimals.
So being quadrant 1.
That's quadrant 1. So we got that answer. Where else is sine a positive number?
Quadrant 2.
I mean, I didn't show you what that comes out to, but if you just trust me, negative 1 plus root 37, and then divide by 6, it's positive, 0.84. It's a positive number. So we got an answer here. That's my other answer. What's my formula in this quadrant?
1a minus reference angle. Or pi minus reference angle.
Pi minus my reference angle. Yep. Because we're thinking in radians. So pi minus my reference angle, 2.13. There's my two answers from that one. Now, we still have to look at the one on the right. We didn't type that in. Let's type in just the argument first. negative 1 minus root 37. Negative 1 minus root 37 divided by 6. That's negative 1.18. I now need to take the inverse sign of that number. I'll type in
We
some
won't be able to,
extra decimal places. Yeah, why not?
because it's over -1.
That's not between negative 1 and 1. So when you try to do that, there's no answer. So we don't have to worry about anything else there. So those are my only two answers. Any question on that?
How do we get to 2.13?
We subtracted our first answer from pi. Now, if you weren't sure, like, if you're wondering how did I know that it wasn't going to come out to a nice answer? Well, if you type in what we had on the left and divide by 6, no, it was negative 1 plus root 37. If you look at that number and then divide by 6, is that 1/2, negative 1/2, root 3 over 2? No, it's not any of those numbers. This is not a number that ever came up when we did unit circle. 0.847. No. So that's how I knew it wasn't going to come out to a nice answer. Okay. Everybody know what kind of numbers you're looking for nice answers? The root 3 over 2, root 2 over 2, 1/2, 1, 0, negative 1.
It's anything that shows up in the coordinates.
Anything that shows up in the coordinates for the 30s and 60s and 45s. Yep. Okay, so a little bit different because you had to use quadratic formula, but pretty similar before that. Do the substitution, get it equal to 0. Okay. So any questions on the type where you got something squared on one side and then something not on the other? That's pretty much the same thing again. Let's try this one. It says find all solutions in one period. Okay. So generally, the first thing we always want to do is get this equation set up so that it's equal to what?
0, 0.
Get it equal to 0. It doesn't matter, but I would move everything to the left. Why? I always like, again, we like that highest degree term to be positive, right? And I know I'm not substituting for that. I've never told you today, substitute for the thing raised to the 4th power. Never. I've always said to substitute for the thing that's raised to the 2nd. So always keep the highest degree term positive, and this time it's not a 2, it's a 4. So keep the 4 right where it is. So minus the secant squared and minus the 1. Okay. Now, they're not all the same trig function. We always substitute for the one that is squared. We're going to hope when we substitute for that, we automatically get tangents in the whole problem. If we don't, then you're not going to be able to do it. Does anybody remember the Pythagorean identity that has secant squared in it?
1 plus tangent squared x.
Equals,
Secant squared x.
yes, secant squared is equal to that. So we're going to change our secant squared to what I have circled on the left. 1 plus tangent squared. So yeah?
Would it be negative because we have a negative secant squared?
Yeah, so I'm just going to leave that negative in front. So this is how I'm going to do it. So I'm going to leave that negative in front, and then I'm just going to substitute for secant squared. I will have to distribute that negative when I'm done. Okay, so let's distribute and see what we get. So we've got 3 tangent to the 4th x. What's negative times 1?
-1.
So we have -1 and another -1. How much is that? -2. I want that at the end. I always want the constant right there. And then what's negative times tangent squared?
Negative tangent squared.
Now we have all tangents. That's good. Now, that one doesn't look like a quadratic, but it is. You can factor it just like it's a quadratic. Whenever you have something raised to a power that's been doubled, plus or minus the same thing that's in that box, raised to half that power, and then at the end you have plus or minus a constant, that is a quadratic type of problem. Whether this exponent is a 6 and that's a 3, that's a 2 and that's a 1, that's the standard quadratic, or in our case, that's a 4 and that's a 2. If that exponent is half that exponent, and you've got the same thing in each of those boxes, and a number at the end, you can factor it just like it's a quadratic.
Will it always be like that?
If I give you 3 terms, yeah. Like if this was tangent to the 4th and this was tangent cubed, could have some problems. So it would always be half. So you'll be able to factor. And if you have trouble thinking of factoring it with tangent, okay, then temporarily don't. Just factor that. Yeah?
So would tangent to the 6th and like tangent to the 3rd also work?
Yeah. Yep. What's going to be my first term in each parentheses when I factor this?
X squared.
You're going to have an x squared and a,
3x squared.
yeah. It always uses this. You always use that to do your factoring. That's the exponent you use. And then in this case, you've got a plus and a minus. And what are 2 numbers that multiply to give me 2?
1, 2.
1 and 2. And if I multiply that out, I get 3x to the 4th minus 3x squared plus 2x squared. What's minus 3 plus 2?
-1.
-1. Perfect. So that's how we're going to factor ours. Except instead of x, what are we going to have in place of that?
10.
10x. Yeah. I'm just going to move this over here. So we're going to factor it as 3 tan squared x plus 2 and tan squared x minus 1. Now what do you do with each factor? Yep, set them equal to 0. So we have x plus 2 equals 0. Tan squared x minus 1 equals 0. And how would you get tan squared by itself there?
Take the inverse tan squared? Or no? Take the square root.
Not yet. We are going to take the square root though.
Minus 2.
Minus the 2 first.
Divide by 3.
Divide by 3. Now you could try to take the square root to get rid of that exponent of 2. But what's going to happen when we try to take the square root of what's on both sides? Yeah?
The minus is going to make the square root like not real.
Right. If you try to take the square root of both sides, it'll get rid of the 2 for the tangent squared, but then you try to take the square root of a negative. That's imaginary. So that means that part has no real solution. We're not interested in imaginary solutions. So that's kind of nice, because now we can forget about that half of the problem. Now, let's focus on this part. What will tangent squared x equal? 1. What kind of number is 1?
A nice number.
How about, well, what's your next step?
Take the inverse.
Oh, you square root it.
you square root it.
Square root 1 is 1.
And 1 is a positive number. So we can take the square root of that. So when you take the square root, okay, that's gone. And what do you get on the left?
Tangent x.
Tangent x. And what do you get on the right?
Wait,
What's the square root of 1?
one.
Plus or minus 1. That just split into two problems. Plus 1, minus 1. So even though we got rid of part of the problem, it just split again. Because when you take a square root, you always get two answers. Now, how are you going to get rid of tangent?
Take the inverse tangent.
Now we can take the inverse tangent. So, well, just trust me. If you take the inverse tangent of 1, you get 45 degrees. Is 45 degrees in a quadrant or on an axis?
Quadrant.
It's in a quadrant. Where did we just get an answer?
Quadrant 1.
Quadrant 1. Where else is tangent positive?
Quadrant 3.
Quadrant 3. They said that, for whatever reason, they want answers between negative pi over 2 and pi over 2. Is quadrant 3 between negative pi over 2 and pi over 2? No. This quadrant, the red zone, we're not going to go in the red zone. It's not between negative pi over 2 and pi over 2. Is sine, this is pi over 2, this is pi. Is this area above it between negative pi over 2 and pi over 2?
No.
No. So if you have any answers on this half of the diagram, they specifically said they don't want them. They only want answers here.
Okay. Yeah, because the opposite if you're going out, say would be negative pi over 2.
So we've got the 45. Yeah, this is negative pi over 2 down here, which is the same as 3 pi over 2. So this is good. Anywhere in the green box, we are allowed to give answers. Outside the green box, they said they don't want them. So we don't do them. So you're done with the first problem. Right? Let's try inverse tangent of negative 1. But I said to do it in degrees because we know it's a nice answer. So again, see, does anyone recognize what that is? Maybe not. But negative 45, you'll see that's a nice number.
It's just the opposite.
And that's between negative pi over 2 and pi over 2. Okay, negative 45 is like right there. What is 45 degrees in radians? Yep. And what is negative 45 degrees?
Wouldn't it be negative pi over 2?
Yep. So even though there are two other answers to this problem, they don't want them. So if you accidentally wrote the other answers in these quadrants, 2 and 3, I'd probably take off 2 points because you wrote 2 answers you didn't need to. I'd still give you credit for everything else, but you'd probably lose 2 points. Any question on that? Yeah.
So those are how the answers have to end up just in radians?
Yep.
For every problem that's like this, they have to end in radians?
I think almost every problem they ask for the answers in radians.
Okay.
Yep.
Will you state if you're in degrees?
Yes. Yep. All right. So that's that one. I don't want to do that one. Okay. Let's. That's a double angle. That's a double angle. Let's do this double angle. So I told you there was one other identity we were going to use today. We haven't used it yet, and that was. Let's see.
Let's see.
That one right there. The problem with this one is not that you have different trig functions. You don't. You have all signs. But if you have all the same trig function, and these are not the same, then who cares? Doesn't matter that you have all the same trig function. That doesn't help. You've got to have these the same. So you are not allowed to have a 2 in front of the x. What's the formula that gets rid of the 2? Well, first, could you just take the 2, throw it in front, and say, yeah, we're good? No. No, you can't just take the 2 and throw it in front. That
It
doesn't
would
work.
be 2 sine x cosine x.
Okay, so 2 sine x cosine x equals sine x. Yes. Now, you might think, well, wait a minute. Now we got different trig functions. Yep, now you do. But you had to get rid of this 2 in front, and there's no other way to do it. Okay? So now let's go through it, like we don't always do. What do you think the next step would be in that equation?
Make it equal 0.
Make it equal to 0. Yep. I would put everything on the left. How are you going to bring sine x over to the left?
Subtract sine x.
Subtract.
Then would 2 sine x become sine x cosine x, right?
Well, this is like having 2xy minus x equals 0. These aren't like terms, because this is different than that. So these can't be combined. But there is something you can do there. And I mentioned this, was the very first thing I mentioned when we started the notes. One of the first things. What can we do with this left-hand side in one word?
Oh. Factor?
Factor, yes. Yep. So we want to take that left-hand side and factor it. Is it the complicated kind of factoring? No. It's a simple kind of factoring. It's right here. That's what you need to do. Pull out the GCF. Okay. So it's actually going to be easier than the last couple problems we did. Okay. What can we factor out from each term? This one and that one.
X. Or wait, no.
Sine x.
Sine
Okay. If you factor it out of the first term, what's left?
2 cosine x?
2 cosine x. And what if you factor sine x out of the last term?
Just a 1.
Just a 1. Okay. So now your factoring is done. What do you do with each factor?
Set it to 0.
Set it to 0. Okay. Setting that equal to 0, that's good. What do we like about setting something equal to 0 when you take the inverse sine of 0? We know the answer is going to be where?
On the line.
It's going to be on an axis, so we don't have to worry about the ASTC. And how about when you set this one equal to 0?
Isn't there a 2 in front of it?
Well, once we set it equal to 0 and move everything, what
It
would
would be
we
1/2.
add the 1 and divide by the 2? Is 1/2 a number that comes up with the unit circle?
Yes.
Yes. So we're definitely going to get nice answers, which means we want to do everything in what first?
Degrees?
Degrees. Do it all in degrees. Even though I know they want answers in radians, that's fine. Do it in degrees. Okay, so I'm in degrees. Inverse sine of 0, well, that's just 0. And that's on an axis. There is no referencing. Okay, so you're done. Now this one, how are we going to get rid of cosine?
Take the inverse cosine.
Take the inverse cosine of
1/2.
1/2, or I just do 0.5, it's less buckets for me to type. 60 degrees. I think we did this one already.
Yeah, it's pi over 3.
It was 60 degrees, or, yeah, you're in quadrant 4, which is 300. And yeah, I remember, because it was 5 times as much.
Yeah, pi over 3 and 5 over 3.
So because there's only so many different angles you can have that are multiples of 30 and 60, you might start seeing repeats of answers once you do enough problems. Okay, so 0 degrees, or technically I should write my answer in radians. 0 degrees, 0 radians, same thing. So 0 radians, pi over 3, 5 pi over 3. Okay. So I think there's only like 3 questions in the homework that are going to start you off at the very first step, like that. At least 7 or 8 of them are going to start you off either with something factored, or they're just going to start you off with a single equation just like that. I think that's the first 6 questions. Just a single trig function equals a number. No factoring, just inverse trig right off the bat. Okay. So they're not all problems you have to do from scratch. I think it's 14, 16, and 19. Those 3 you got to do from scratch. All right, so we'll take a look at the 14 questions. We'll look at those tomorrow. And if you get this section, then I think you'll be good for the rest of the week. Tuesday, Wednesday, and Thursday is much, much easier.